L34, we are going to cover and refresh our memories on how to do electron configuration. Okay, so we can use the quantum mechanical model of the atom to show how the electrons are arranged in the hydrogen-like atomic orbitals of the various atoms that account for the organization of the periodic table. Our main assumption here is that all atoms have the same types of orbitals as have been described for the hydrogen atom, which is still the kind of basis for the quantum mechanical model today. As protons are added one by one to the nucleus to build up the elements, the electrons are similarly added. This is called the Aufbau principle, which in Chem 1, if you remember, we had the arrows sheet that helped us with the Aufbau principle. You do not get this on the AP exam, so we are going to have to be able to do it by just looking at a blank periodic table, okay? And I can help you more in person with this too if you need to. So, to fill in orbitals, like we have the 1s, 2s, 2p, 3s, 3p, 4d, all those kind of things, we are filling each orbital with 2 electrons, and then we move on to the next one, okay? So, as we go, and should be just review from Chem 1, we use the arrows from the spin number to show how many electrons there are. So we look at the atomic number on the periodic table for each of the elements to know how many electrons they contain. So for hydrogen, for example, it has the atomic number of 1. So that means we have 1 arrow. And then it's pointing upward. Well, now for helium, it has 2 electrons. So the first one goes in where hydrogen's was, but then the second one gets pointed in the opposite direction in the same orbital. So that's showing that 2 electrons, opposite spin, fill up the 1s orbital. Okay? Well, now we get to lithium. Lithium has 3 electrons. So the first 2 are just like helium, but now that's full, so we move on to the 2s, and we go back to pointing upward. Okay, and then beryllium has 4. So 1, 2, 3, 4. The second orbital, 2s, has 2 electrons of opposite spin, so now that is full as well. I hope that you guys are seeing the pattern. Once we get up the 4, so then for boron we have our 5th one go on the first line of the P's. Okay? And we could keep going with this if we wanted to, but we're not going to be doing orbital diagrams, so we don't need to really practice that. Okay? We are going to be doing the electron configuration instead. So, the pattern is helping us with this electron configuration, okay? Where the hydrogen had one arrow in the 1s, so it has an electron configuration of 1s1. Helium had 2 electrons in the 1s, so that is 1s2. Lithium had 1s1, or 1s2, but it also had 2s1, so it's ending with that. So are you noticing a pattern here? We could keep going and going, where we add 1 electron to the outermost orbital when we do that. This type of thing is very similar, and it explains that similar properties that Mendeleev saw when he was organizing his periodic table. Okay, so instead of using the arrows, we can write electron configurations by looking at the ends with the periodic table. And I'm going to be posting this online for you, or I have paper copies left over from years previous, where as you go across, the energy levels down, we have 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, like that, all the way down. And this is how you fill in your orbitals, okay? If you need to watch the electron configuration song, it's also posted online for you to watch that too, which I know that's everybody's favorite, right? So this again is just another picture of that, where the boxes across, you start with 1 at the farthest left and then you count all the way up, where the s's can hold 2 electrons, the d's can hold 10 electrons, p's can hold 6, and f's can hold 14. So this is the reason why our periodic table is in this weird shape, is because of electron configuration. That's the whole point of it, okay? So we're going to go through how to do normal electron configuration quickly, and then we'll also go through noble gas. And on tests and quizzes, it's your choice. Whichever you like better, you can do. Okay? So for the normal electron configuration, we are going to just do it for neutral atoms today, but you might be thrown in an ion in the future, so be careful with that, okay? But so for neutral atoms, we just look at their atomic number. So for K, potassium, that has 19 electrons. So we are done when we have 19 electrons accounted for. So starting up with hydrogen, that's our 1s. And there's 2 electrons in the 1s, so we got to move on. That's 2 electrons down, 17 to go. Next we hit the 2s. So then we have 2s2. After 2s, going across horizontally, we hit 2p. And p's can hold 6. So now we're at 10 electrons, 9 to go. After 2p, we have to go to the next line, and in the next line down, we have 3s2. And then we have, after 3s, skip the gap and go to 3p6. So we are now at 18 electrons. We only need 1 more. Well, next, after 3p comes 4s. Sometimes people think 3d comes next, and it doesn't. It's 4s. And we only need 1 more electron, so instead of putting a 2 down, we're just going to put a 1. So it's 4s1 is the ending point for the potassium. Okay, next we have phosphorus. Has 15 electrons, so it's going to be shorter than what we just did. So we start back up with hydrogen, 1s2, go down to lithium, 2s2, skip the gap, go over to boron, 2p6, gets us to neon with 10. Now we only need 5 more. So then after 2p6 we have 3s2, gives us 12, and then we're hitting the 3p as next. And instead of writing 3p6, we only need 3 more electrons, so it's going to be 3p3. Last one, neon, has 10. So starting with hydrogen, 1s2, go next to lithium, 2s2, and next is 2p, and we need a total of 10, so we're going to write down the full 6. Okay? Hopefully this is not something that's really out there you can really catch on and really fast, because we've done it so much in Chem 1. Okay, so that's how we do our normal electron configuration. At this point, it's important to review the concept of valence electrons, which we're going to talk more about that in chapter 8. But valence electrons are the electrons in the outermost principal quantum of an atom. So if we're looking at an electron configuration, like for example for the neon, it was 1s2, 2s2, 2p6. The first number signifies the energy level that the electrons are located in. So valence electrons are in the outermost energy level. So we have as our outermost energy level the second energy level, and we have a total of 8 electrons in that energy level, 2 from the 2s plus 6 from the 2p. Okay, so those are our valence electrons. Everything else is known as core electrons. So in this case, the 1s2 contains the 2 core electrons. Okay, so that's just important to know, because we can kind of use this idea for noble gas configuration instead, where we can take off a bunch of those core electrons so we don't have to write them down, and then instead just write down some valence electrons that are left over. Okay? For noble gas configuration, we have our shorthand way, where you find the closest noble gas with the closest number of electrons that does not go over. Remember, noble gas column is group 8A on the periodic table. So if you're ever putting something in brackets for noble gas configuration, it can only be helium, neon, argon, krypton, xenon, or radon. Nothing else can go in the brackets. And that's because they have a completed octet. They have 8 valence electrons, kind of like we just saw with neon. Okay? So let's just practice. We did phosphorus up above, so we know that phosphorus has 15 electrons. Well, the closest noble gas that doesn't go over 15 electrons is neon with 10. So I'm going to go ahead and put neon in brackets, the symbol for neon. So that's accounting for 10 electrons that have already been accounted for. We don't have to write anything down up to that point. Now, we just keep going after wherever neon left off. So if neon is in the second row down, and it's in 2p. So that would be ending with 2p6. So I'm not going to write down 2p6. I'm just going to jump ahead and keep going until I get my 15 electrons. Sometimes in Chem 1 I tell you that you can write the number of electrons from the noble gas up above it, so it helps you with counting. So you can do that again if you need to. So to keep going after neon, next comes 3s2, because we are down with the sodium. And then we need to keep going because we need 15, and that's only 12. So then we end with 3p3. And this is a case where the valence electrons are all showing outside of this. Okay? And that's it. So now for calcium, it has 20 electrons. The closest noble gas that does not go over is argon with 18. So I'm going to go ahead and put argon in brackets. And that's 18, so I'm not going to do anything before argon, but I'm just going to write what comes next horizontally in the next row, and that would be potassium, so that is 4s. But we need 2 more electrons, 4s2. Which if you looked at an ends with periodic table, calcium would end with 4s2. Okay? Last one is tin, Sn. And this is when noble gas configuration is really great because you don't have to write down those 50 electrons, right? So the closest to 50 that doesn't go over is krypton with 36. So after krypton, next comes rubidium, which is in 5s. So we have 5s2. And then after 5s2, we go to D, and that is 4d10. That's the hard part to remember, is the D's that are kind of off whack. And then we're in the 5p, and tin will end in 5p2 because we need just 2 more electrons to make 50. All right, so that's our noble gas configuration. You can do either way you want. I think on the level 34 worksheet, I have you practice both just so that you get this back into your mind, how to do it. And don't forget those last questions on the other side of the worksheet. Please ask me if you need more guidance in class for this. So let your heart